So what we are going to start is chapter 3, motion in. So we are going to in simplest cases study our mechanical system. Since we last time, अगर आपको याद है, we started with Lagrangians. We had a definition of Lagrangian. So in the simplest cases, we defined how we define Lagrangian of a system, and we substituted, or we had an alternative way of defining mechanical systems. The way we studied in your earlier class, kinetic potential energy. In our so we had our understanding of Lagrangian of a system in the simplest cases. अब इसमें ये है कि we had defined Lagrangian of a system was defined. So you can define it like this: 2 dot square minus mu t. So here this Q is some generalized. So what do you mean by generalized coordinate, Shabash, if you remember? So generalized coordinate we had in Lagrangian system. One is normal coordinate system, जिसमें 3 coordinates होते हैं. But हमने कहा कि once we why did we take recourse to Lagrangian system? Because the motion of the system also depend upon the orientation and different coordinate systems. So depend upon our choice of problem, we set a given Lagrangian. So before we are going to set a given Lagrangian, we have to specify its coordinates. So in Newtonian mechanics or in the classical mechanics, the way we define in your earlier classes, the simple Cartesian coordinate system, we are not bothered, even though we could take components of those coordinates, vector components. But here we have a specific way of assigning coordinates before we are going to set a given Lagrangian. So that we denote in terms of generalized coordinate system. It helps us into setting a Lagrangian from problem to problem. For example, motion of a bead, which is constrained by certain systems, polynomial system, cyclonomic systems. So these are different terms which are used in the books. Before we are going to solve a given equation of motion, so what is the sort of Lagrangian we are going to impose? And what are the coordinate systems? What is the generalized coordinate system? So that's way we have defined Lagrangian this way. Or normally we say it's we simply say it's the Lagrangian is in the simplest case is the kinetic end. It can be minus or plus. So sign should not. It's some quantity which will come out to be constant. It will come out to be conserved in a given closed system. Which includes this term. So इसका minus भी constant आएगा. The plus will also come out to be some conserved quantity. So that's not the point. So now what we are going to study, if we want to impose, if we say it's plus, the way we study, and if we say that, we also say that mx dot square plus ux is basically what? It's total energy of the system. So it's a sort of differential equation which might be differential equation कहाँ से आ रही है ना? X dot square. So it's dx by dt whole square. So it's rate derivative of displacement, है ना? Position vector. You can see it. So if you want to solve it as a part of a differential equation, it will be basically what? It will be like this. It's E minus ux. तो ये dx dot by dt है square. So it will be 2 will come here. It will be 2e minus ux by m. So since it's square, so it will come out to be root, or it will come out to be when E minus Ux. E minus Ux. Again, if you want to solve it again, so if you want to take a parameter of t and this, if we integrate it, before we are going to integrate it, so we can say it's dt by dx will come out to be, it will come out to be like this. ये है ना, ये हमने इसको ऊपर नीचे किया, so it will come, ये ऊपर जाएगा, so it will be like this. So if you are going to so integrate it, it will be dx by root of this e minus ux will remain here. So if you are going to integrate it both sides, so dx will go here and it will be integration. So this is a different solution of a differential equation in the simplest possible case. This is what. So what if we integration of dt from time t is equal to 0 to time t is equal to 1. So we are going to solve the differential equation from rest, from time t is equal to 0 to whatever time it is. So if it is 0 to t, so it will be t minus 0, it will be, so t, the simplest possible differential equation we have solved is, we'll write it this, dx by e minus ux. But now this is the thing, plus some constant of integration, some constant of, so we have solved a simplest equation of motion in having this our if we define total energy of system in this way. अब यहाँ से what we do, we get in the simplest case, there is a variable of time and there is a constant of integration. The way I said last time, many times before also. So if you have agar Newton's second law hai na, it's also a sort of a differential equation, hai na? You integrate it once, so it will give us velocity. You again integrate it, it will give a displacement. But every part of it will have some constant of integration. It will be C1 plus. So what these constants of integration are? They are basically initial conditions. For example, if the body is at rest, we'll say C1 is equal, it has started from 0. If body has not started from rest, it has already some velocity. You are going to take it that, है ना? तो those, अब ये ना एक physicist है, there is a physicist James Jeans, शायद उसी का नाम है, I don't remember exactly name. उसका एक statement है कि whole physics अगर है, it is solving these differential equations and it's basically solving, these are boundary value problems. Whole physics can be reduced to solving boundary value problems or different boundary value problems. क्या है? You should know the constants of integrations क्या है, C1 plus. तो फिर हमारी जो equation है, it will be, our information about the system will be complete. Then we can predict a system, जो हमने start में किया था. We can determine a system. Given a particle, you have initial conditions, you have boundary conditions. After 5 seconds, you exactly will know वो कहाँ पर जाएगी. कोई planet यहाँ है, 500 साल के बाद कहाँ आएगा, ठीक है? 1000 साल के बाद कहाँ आएगा? Given the equations of motions and given the constant of integration, so initial value problems क्या है? So initial value sometimes we fix them from experimentation, ठीक है? कहाँ से दो, which observation से fix करते हैं, and you differential equation and out you get the equation of motion in, for example, in the simplest cases, ठीक है? So this is it. अब ये है कि always one thing we are going to say. So what we are going to say is basically, for example, we always assume that the potential energy is always less than total energy of the system. ठीक है? So if it is like that, this means kinetic energy is always positive. From this है ना, E minus K plus U is equivalent to E, है ना? So E minus U will be always positive. This means kinetic energy can always be positive. Or potential energy of the system is always less than that's it. So it's merely convention. You can take whatever that is. The more important point is that this kinetic plus potential or kinetic minus potential energy will come out to be a constant thing. So if you assume this thing, then what? So there comes a time जहाँ पर अगर ये है so there come times when if it's K minus U, so there comes time where kinetic energy will be equivalent to the, अगर हमने अब equation of motion निकाल ली, ठीक है, of any system, so there come times, so it will always fluctuate. The kinetic may be more, potential may be less, but at some point in time, the kinetic may be equivalent to potential energy. So that will be sort of a simplest ground state system. So it will be in a simple ground state. You can see it like that. So they might be, they are the turning points of the. Well, अब ये है कि there can be motions of different kinds. You might start from rest and you might come to rest. You might start from rest, or your motion may continue to infinity. Or you might start from infinity, but you might come at rest. Or you might start from infinity and you will go to. So these are all sorts of motions which we are going to study. अब इसी में है कि the point where this kinetic energy and potential energy of these motions, उन्हीं को हम कहते हैं, we call turning points, where velocity is zero. So if we follow the book, he used them. The motions are finite, or if the particle goes from and it can go from start from zero, and its motion can extend up to infinity. And if we want to graphically represent it like this, normally जो motion है, motion, this equation का graph, if you want to just interpret its graph, it will come out to be like this. So motion is normally represented from point x1 to x2. So this is the region यहाँ motion represent हो रही, ठीक है? And this is the point where kinetic energy is equivalent to potential energy. यह है कि it will show sleep. Kinetic will grow, potential will decrease. Potential will increase, kinetic will decrease. That sort of seesaw which we are going to see in this graph. And if we want to see it in terms of whole, अगर हम इसको 360 degree motion में लेंगे, if we want to represent it in terms of sort of circular circular thing, okay? If you want, ये यहाँ से गया, फिर यहाँ से आया, है ना? Complete. You start from maximum kinetic energy, फिर minimum kinetic energy, again maximum, again इस तरह potential energy maximum to minimum to, so there will be 2 cycles. और अगर quadrant पे जाएंगे तो 4 times ये आएंगी. So it will be, if you want to represent this equation for wholly from position x1e to x2e, but you have to multiply it 4 times. If you have to multiply it 4 times, so it will be 2 square. So ये इसके साथ cancel हो जाएगा. So you can it will come out to be like this. Total time period ये 0 to, if you have integrated from 0 to t, full circle जो भी है, which will consider of two oscillations, minimum to maximum, फिर minimum to maximum, है ना? So it will be like this. Root of x1 e, x2 e. ठीक है. Now इसमें ये है कि what this book has shown a simplest one example which I'll just थोड़ा सा इसको मैं just elucidate. It's a solved example, but अब ये है कि normally in your books you might have studied oscillations. So have you studied theory of small oscillations? Study किए. तो small oscillations में वहाँ एक integral आता है, elliptical integral. You have some idea of that. So in simplest cases, whatever motion we study in a pendulum, it's for very जो आप लैब में करते हैं Cater's pendulum, उसमें हम रखते हैं कि the oscillation is very small. So we are neglecting higher order terms in the series, and the first term will come out to be 2 pi root of L by G or root of M by K. ठीक है. But if we want to have a precise expression of that motion, it's an approximate expression. So we have to take recourse to elliptical integrals to solve it. So to simplest case, if we want to produce this motion in one dimension, for example, determine the problem is how can we determine the period of oscillation of simple pendulum, and that's mass suspended by a string of length, mass suspended by a string of length L, M. Normally we take point masses, point mass is also an idealization, nature में mass होता है कुछ, ठीक है. तो then it also helps us later. It's not only oscillation होती है simple mechanical, earth भी oscillate करता है at some point, your eye का socket भी oscillate करता है, but the mechanical oscillation है ना, जो principle है oscillation का, वो same है, ठीक है. जो wings है they also oscillate. अब डिपेंड्स अपन अगर मास ज्यादा करोगे, लेंथ कितना होना चाहिए, ठीक है, स्प्रिंग कांस्टेंट क्या है, सो व्हाटएवर दैट इज. सो अब ये है कि टाइम पीरियड क्या आएगा. सो वी आर गोइंग टू सेट एन लैग्रांजियन एनर्जी ऑफ द सिस्टम, या लैग्रांजियन ऑफ द सिस्टम. तो क्या आएगा, हम स्टार्ट करेंगे m स्क्वायर m, सिंस ये ऐसे है ना, सो इफ इट्स एंगल 5, सो मोशन इज अलोंग this, ठीक है. सो इट विल बी L5 फॉर स्मॉल एंगल्स. एक डिस्टेंस है ना इसका 5 परपेंडिकुलर, ये परपेंडिकुलर हो गया, ये बेस और हाइपोटेन्यूज. सो दिस विल बी L5 फॉर स्मॉल, इट विल बी L cos 5, है ना. बट फॉर स्मॉल एंगल्स cos 5 is equal to 5, so it will be L5, ठीक है. सो the total energy will be 1/2 m L square 5 डॉट स्क्वायर, है ना. चेंज इन एंगल हो रहा है ना, x के बदले क्या है L5, सो L5 डॉट आएगा माइनस mgl cos phi. So if phi is constant, so it will come out to be now the phi value of phi can go from phi is equal to 0 to phi is equal to phi naught, the maximum value of phi. So it can start from phi 0 to ऐसे जाएगा, है ना. So phi, the maximum value of phi, we take it as phi naught, ठीक है. So we can take it that. अब ये है कि जो टाइम पीरियड will come out to be, so if it's 1 2 3 4, है ना, 4 बार आएगा, तो 4 times, so L by 2g angle goes from 0 to, if it's maximum angle phi naught, तो d phi by, actually it's 2g cos of phi. So you are taking angle from cos of phi 0 to cos of phi naught. So you are going to take कि इसके साथ ये है root of, so basically it will be cos of phi 0 phi naught. So we'll write it like here cos of phi minus cos of phi naught. ठीक है. So now you can convert this cos phi into 1 minus sin square phi by 2. ये भी आएगा 1 minus square phi naught by 2. 1 will cancel, so it will be sin square phi by 2 minus cos square phi by 2. So it will be equivalent to like this. 4 को इसके साथ आप करो, it will be 2. It will be 2 है ना, यहाँ root of 2, ये root of 2 square, एक root कट जाएगा तो 2 यहाँ रहेगा अपना. It will be sin square phi by 2 sin square phi by 2. This is phi naught. ये phi naught आएगा ना यहाँ, because I have 1 minus sin square phi by 2. ये 1 minus sin square phi by 2. 1 इसके साथ रहेगा. It will come out to be this. Now what we are going to do, so अब इसमें यह है कि if we इसमें sin phi एक बाहर निकालेंगे तो it will be 1 minus sin phi by phi naught. ठीक है, अगर sin phi बाहर निकालेंगे phi by 2 square, यह आएगा ना 1 minus sin square phi by 2 minus sin square phi by 2. तो इसके बदले we are going to write as this sin square phi by sin square phi by 2, we are going to write as in terms of sin of zeta. We write it as sin of zeta. So if we write it as sin of zeta, तो whole of integral जो हमारे पास, and we can write this integral in terms of k. k को हम ऐसे लिखेंगे. So we are going to take angle from 0 to maximum angle pi by 2. तो k के बदले हम लिखेंगे ये 1 minus k square sin square zeta. So if we write it this, so you can, this whole integral will basically, it will just simplify to writing our integral like this in terms of k, in terms of so इसी को if you go to the books, this is known as elliptical integral. So in the theory of analysis, ये basically Jacobian integral, it's also called Jacobian integral. आप अगर जाओगे books में, if you go to the books, solution of this elliptical integral ये अपने आप में ये है. But here what we are going to use, उसको हमारे इस knowledge को we are going to use it. So अब what we are going, we see interesting thing what will happen. हाँ, अब you just see it here. Interesting thing happens that जो time period हमारे पास आएगा, if you just ये ना 1 minus k square sin theta. अब zeta जो है zeta we are written in terms of phi by phi naught. Phi by, it's the value of phi at maximum and value of phi, normal phi. So in that terms we have defined zeta. ठीक है. अब इसी को if you want to just expand, if you want to open up this integral in terms of sine function, in terms of, so there will be different terms. So it will be as a homework exercise. You just try to expand this integral in terms of sine. And for small angles, phi naught is equivalent to phi. For small oscillations, so it will reproduce to our traditional, जैसे हम अपना पढ़ रहे थे, कौन पढ़ रहे थे? We studied 2 pi root of L by G. ठीक है, so you will see it. सो इसमें ये है, यू जस्ट हैव एन होमवर्क हाउ वी कैन एक्सपैंड दिस इंटीग्रल को कैसे एक्सपैंड, इलिप्टिकल इंटीग्रल, दिस इज अ होमवर्क, ठीक है. द बुक हैज नॉट डन इट, सो इट मीन्स ही हैज सॉल्व्ड द प्रॉब्लम, इट मीन्स ही implores upon you to go to this thing. अब इसमें in literature it is also called Hamilton-Jacobi integral, elliptical integral. So when you study theory of small oscillations, so it's not an, जो हम पढ़ रहे हैं book में, it's an approximate formula. If you want to take smaller things into considerations, so this is the more precise formula. If you want to take smaller motions, okay, the more exact formula is this. In simplest cases you can reproduce it, and you can also see in the lab जब आप करते हो, है ना, 20 minutes के लिए करते हैं ना वो ग्राफ बनाते हैं Keter's pendulum के लिए बनाते हैं ना. So but if you want to do it more precisely वो experiment, ठीक है, you can include these higher order terms. Got my point? Sure.